Bismillahirrahmanirrahim. This video is from Signals and Systems book by Mr. Oppenheim. And here we'll be discussing example 9.6. And this is on the request of a student. Before going to the question, some of the properties we should discuss. The region of convergence for a Laplace transform has a couple of properties. The first one is that the ROC, or the region of convergence of XS, consists of strips parallel to j omega axis in the S plane. So let's see what does he mean. If this is the signal, because of the UT, it is right-handed signal. This transform is in this form, and because the real part, real of S, is greater than negative of real of A, because it is right-handed, this is representing pole. S plus 1 is equal to 0, means S is at -1. So this is the pole position. So we draw the pole line. And the right of the pole line, we can steady draw vertical lines, whatever. So this whole thing will be the S plane. So this is the plane for the signal x1t, which is right-handed. Now, if the signal is left-handed like this, we get the same formula, but because it is left-handed, therefore, we first of all from here S plus 1, S plus A is equal to 0. That means our pole is at S is equal to -1, and the shaded line should be now the vertical line on the left. So that is what he's saying. Consists of strips parallel to j omega axis. Now this is j omega axis. So all our strips should be parallel to this. So this is the meaning of the property number 1. Now the property number 2 says that for rational Laplace transform, or a rational function which is of this form, the ROC does not contain any pole. So the ROC cannot have any pole inside. Even in the previous two examples, we saw that the ROC was either right of the pole or left of the pole. Same will be here, that if it is a rational number and we can have two poles, not necessarily because of this, but two poles, then our ROC will be in between the two poles. This is what he's saying, that the ROC does not contain any pole, no pole in the ROC. Then the third property is saying that if xt is a finite duration, like this signal is a finite duration, and is absolutely integrable, so if it is not unbounded, it is integrable, then the ROC is the entire S plane. Then there will be no poles in this, and the whole S plane will be the region of convergence. And now let's see this example, 9.3. Prove that ROC includes the entire S plane. So this is the given signal, and we can see that the limit is from 0 to capital T. So we can draw it like this. This is the decaying signal, and from 0 to 2, capital T is the limit of the signal, or the value of the signal. And now to find its Laplace transform, I hope you remember this formula. It is defined as integral xt est. In our case, we'll write e at and e minus st, and the limit, instead of minus infinity to plus infinity, will now be from 0 to capital T. These two we can add, and then integral, I hope you remember that we can take the power outside. So we have taken this, and then e power remains, and then we put the limit from 0 to t, and now putting the values t here and 0 here. This will become 1, and this minus multiplied by minus, we get this equation. So we were here. Now, since in this example, xt is a finite length, it follows from property 3 that the ROC should be entire S-plane. But what is, look here, look, this looks like a pole. But in equation 9.42, S would appear to have a pole at S is equal to -1 from here. And we have learned from property 2 that ROC does not contain any pole. So if there is a pole, that means this is not correct. From property 2 would be inconsistent with the ROC that consists of the entire plane. But there is a trick, actually. If we look this carefully, we bring this to the numerator. And now if we put the value of S is equal to -a, then you can see the 1, E minus -aa, here also -aa, and this becomes 0, this becomes 0. 0 and e raised to the power 0 will also become 1. It is 1 minus 1, and it will 0 over 0, which is an undeterminate case. So first of all, we could not find a pole. There is no pole, but this is a unique situation. It has become undeterminate. So what do you do? For such type of a case, we use what is known as L'Hopital's rule. And the rule says that there is a general method of evaluating indeterminate form, such as 0, 0, which is here, or infinity by infinity. What is that method? It says if we are taking limit of the function divided by another function, and if you have this 0, 0 condition or infinity condition, you can still find the answer by differentiating the two and then taking limit. So let's follow this rule. We differentiate and then take limit. So differentiating the numerator and the denominator. And from here, you can see differentiating with respect to S. That will be 1, this will be 0, this will be 0, 1, then it will be minus dds and ESAT. Now, since we are differentiating with respect to S, therefore this t is a constant. It will come out just following this formula. Dex is a comes out, and then e raised to the power ax. In our case also, it will be t will come out, then e raised to the power minus sa t. And there will be sign change when we differentiate. This sign will come here, multiply. Okay, same thing. And now if we put the limit for s is equal to -a, we get this term, and plus, now this when you add will be 0 power, so e raised to the power 0, 1. So the final answer of the limit is t, and t does not have any pole, anything. It is simple, a figure, a number, and therefore we conclude from here this is equal to t. That means the entire S-plane represents our signal limit xs is equal to -a. I hope you have been able to follow this. Please let me know through your feedback. Thank you.